This session is going to be about ramps, work, and energy. So let's start off in the middle here. Let's talk about work to begin with. Well, and energy, because they're all related. We're all familiar with energy. There's energy of all sorts of different types. We can have nuclear, right? And we can have acoustical, thermal energy, heat. You may say, well, what does energy look like? Well, it's actually invisible. Nobody's ever seen energy. There's chemical energy. We get chemical energy out of gasoline. There's just all sorts of different types of energy, and we have a sense of what energy is. This country has energy needs. We consume energy when we toast our toast and things like that. But the main issue is that energy is defined as the ability to do work. Energy is often, in SI units, we say energy is given in terms of joules. It's named after a fellow named Joule. And a good way to think about energy, in fact, I often ask about this, is to think that 1 joule is about as much energy as your heart uses. Your heart uses when it beats 1 time. 1 time. So a joule really isn't that much energy. Now, a joule is actually an alias. Remember, that means an abbreviation for a more complicated set of units. In this case, it stands for kilogram per meter squared per second squared. Will I ever ask you to remember that? No, of course not. It just means energy, right? And this is what's embedded inside it. Just like before we saw embedded within newtons, which is the unit for force, it has kilograms per meter per second squared. Does that mean anything physically? Not really to me. Maybe, I sneak in there mentally this idea of mass times acceleration, right? Which is what it is. This actually also, and again, this is just for your edification only, not for tests or anything like that. This also stands for pascals per meter cubed. And you're going to learn later on that Pascal is just a unit for pressure, much like pounds per square inch. And so joules is actually energy density. So it's energy per cubic meter, or it can stand for watt seconds, right? This is watt. That's a unit of power. And again, this is just all sort of trivial background information for you. And for more trivial background information, we can say that 1 nanojoule, what is that? That is a 1 times 10 to the minus 9, which is like so incredibly tiny that let's get 0.00000, let's see, 3, 6, 1, 2. There, that's how big that joule is. 1 nanojoules is about 1/160th of the kinetic energy of a flying mosquito. So that's, or how much they would be using. per second, right? And so anyway, if you had 1,000 joules per second that you were using, that's or that you were receiving, that's actually the amount of solar radiation the Earth receives per square meter. So you could see, if we could kind of scoop up all of that energy using some kind of very clever engineering device, we could actually get quite a bit of energy just from the sun. Now, I also want to talk about another unit of energy, and this one is called the calorie. We all know about calories. And a calorie, as it turns out, is the amount of heat. 1 calorie is the amount of heat it takes to heat 1 kilogram of water by 1 degree Celsius. Now that makes sense. Okay, so that's 1 calorie, and as it turns out, there are 4.186 joules in 1 calorie. So that means if you have something like a 100 calorie apple, right? So your body could get 100 calories of energy out of it. It actually is something like a 400 joule apple that you would be eating. So I guess, let's see, one last little type of energy I want to put right here is kinetic energy. That's energy by virtue of something moving. And so all of these types of energy, really, they just use the same unit, which is a joule, and they're just different ways of carrying energy. When you get down to the very bottommost idea of what is energy, it always relates to the idea of some molecule moving, right? Or some portion of a molecule moving. And so you can either have a car, right, that is moving and it has kinetic energy by virtue of its motion. But even when the car is stopped, what's happening? Well, you've got these little metal atoms, right, in the car. And those metal atoms, they've got electrons rotating around them, right? So you may have an atom, it's got electrons rotating around it, and even the atom itself is kind of wiggling around. So even when the car is still, it's still got some kind of energy affiliated with it. Only if you took the car and froze it to absolute zero, so that absolutely nothing moved, could you get rid of a lot of the energy. But there's still energy associated with just having mass. The bottom line of what I want you to remember, though, is just this idea that we got energy, we measure energy in joules, just like we measure force in newtons. Now, energy, so we've got energy. As it turns out, that's in joules. Work is defined, it is in joules, and work is defined as being a force through a distance. So if I take a box and I push it, through some distance, maybe 5 meters. And so the weight of this box is going to be, well, actually the weight doesn't matter. Let's see, we're going to put our force. Say we have a force of 10 newtons, and we push this box using a force of 10 newtons. We push it 5 meters. Then the work that we would do on that box would be force through distance, and it would be 10 newtons times 5 meters, so it would be 50 joules. Okay, so that would be how we could calculate how much work we've done. Now I want you to remember that work is directed energy. So you can see, look at this. It goes in one direction. We've taken those molecules and we move them all in one direction. Heat is randomly directed energy. And by that I mean, what is heat? If you start, let's see, we've got a pot of water. Okay, there's our water right there. We've got green water. Okay, well, we'll make a nice red flame anyway. Okay, so there's our flame. What is that heat doing? The heat is going in, and it's actually it's causing these molecules in the metal to start vibrating a little bit. And when these water molecules come down and they hit against that metal, well, it taps them and it gets them to moving. So the water that is warming up is starting to vibrate even more and more. And we're going to talk about that later on. But the way it vibrates is just, it's motion. It's randomly moving. Some of it comes, well, a lot of it goes up a little bit, right, because it's convection. But it's causing these things to just sort of vibrate around, and it's doing it completely randomly. That's why we call heat randomly directed energy, while work is directed energy. Now, your book talks a little bit about the idea that energy can be, often we think of it as kinetic energy, which I'm just going to write as KE there, or potential energy. And potential energy is, well, kinetic energy is energy by virtue of motion, and and potential energy is energy by virtue of position. And you think, oh, okay, well, we can all see that, a car that's going at, 50 miles an hour, boy, that's a pretty bad looking car. Okay, now runs over here and it bashes into some brick wall. All of a sudden, we're going to see the results of that car bashing into the wall, right? So we can see the kinetic energy as it gets dissipated by hitting the wall. And a lot of that will come out as heat, breaking things, and so forth. Similarly, potential energy, there's a lot of energy stored there. I'll give you an example. When I worked in Antarctica, there was a sort of this big entranceway into like this hall-like, well, it was a big like tube. And what people would do is they would take bulldozers and put snow down this tube, and it would come down into this, and it was kind of like a big garage where the snow would come out here, and then there was a big garage door opening sort of, and you could walk inside and shovel the snow out, and we'd take it in and we'd use it to cook our meals and so forth, go into the mess hall. Well, there was one guy, he used a shovel, and he dug out the whole area under the sort of like about the size of a, I don't know, maybe a little less big than a big garage, but he dug it all out. And so the snow was packed in, and he couldn't reach up above. It was all packed in here, and it was held tight because it was frozen sort of to the walls. And so he dug this all out, and then he had like this big tunnel with a hollow, or it was hollow in here, and then up above there was a big, actually,
Avast virus database has been updated.
Now you can see my Avast has been updated. But anyway, so this is he had a big, massive block of snow that was compacted above him, and what he did was he whacked it with his shovel to see if he could get it to fall down, and it did. It all fell down right on top of him, and it actually sort of deep sixed him. So anyway, that was indeed a whole bunch of energy, potential energy, by virtue of the position of the snow up above his head. And when it fell down, that energy was released, and that was sort of to his undying chagrin. Now we can calculate potential energy. We usually calculate it using this formula. Potential energy is equal to m times g times h. So let's say that that mass was, I don't know, call it 1,000 kilograms. And, well, we know what g is. It's the same gravitational potential. So we're going to abbreviate that as 10 meters per second. And let's say that that was all, I don't know, just for the sake of argument, 3 meters above his head. So the particular above you will be saying, or among you will be saying, well, wait a minute, some of it was more than 3 meters above his head, but we'll just say, we'll kind of average it as being 3 meters. Well, look at this. The amount of potential energy in all of that would be, let's see, 30,000 joules, right? Would be the amount of potential energy stored up there on top of this guy's head. And of course, that's quite a bit of energy. So that's how you would calculate something like that. As far as kinetic energy, how do you calculate that? Let's see. We can calculate kinetic energy by saying that that is 1/2 times the mass times the velocity. And what makes it easy, and I'll make everything easy for you in this course, velocity, you always want it to be in meters per second. Don't put it in miles per hour or something like that, but I always give it to you in meters per second, so that's okay. Mass is in kilograms, and so then you can work easily. So if you had a car that was going at, let's take a car at a velocity of 5 meters per second, which is pretty fast. And to calculate the kinetic energy of that car, 1/2 mv squared. So it's going to be 1/2, and we'll call that car, just for convenience, 1,000 kilograms. I'm always using that. And then times 5 meters per second squared. And 5 times 5 is 25, right? So this is all going to turn out to be, 1/2 of 1,000 is 500. And then times 25. And so then that all turns out to be 12,500 joules would be in that particular car that was going at 5 meters per second. Oh, that's pretty much. In fact, that could be enough to do quite a bit of damage to a person, so we wouldn't want to hit a person with a car that was going that fast. Okay, now let's tie together some of these ideas. What if we happen to have a ramp? Okay, so let's draw a ramp. Okay, so we're going to take it. Here's our ramp. Now let's say that we had to lift a brick straight up. Zoop. Okay, and I'm going to make my ramp 1 meter high because that just makes everything easy if I do that. And we're going to call this, let's call it 2 kilograms. That's the mass. Okay, so that's the mass of my brick. Mass of brick. Okay, now the weight of the brick, is going to be 2 kilograms. Well, you know, we know that weight is equal to m times g, so we'll say it's equal to the mass times, and again, I'm going to be lazy and approximate things as 10 meters per second, right? Because that's g in approximate form anyway. And so it's going to turn out to be 20 newtons is the weight of this mass. So I'm going to do a little bit of erasing right here. Erasing. Okay, there we go. Okay, now the weight going down is 20 newtons. So that makes sense that for me to lift this mass up, it would take me, well, I'd have to push it with at least 20 newtons, right? To push it up, because that's what I would have to oppose the weight with. We could get a little bit tricky and say, once I started pushing, I'd have to push it just a little bit more to get it to accelerate upwards, but then it would just go up at a constant velocity. So anyway, if I look at this thing and I say, what is the potential energy needed to have it lifted up to the top of the ramp. And that's just if we're doing it straight up. That's all we're going to do, is we're going to lift it straight up. It doesn't really matter whether the ramp is right there or not. We just want to lift it straight up by 1 meter. Well, we already know the potential energy. In your book, they call that U, and that's often the case, but I often just call it PE because it's easy and straightforward, is equal to m times g times h. Now look at this. M times g. What is that? That is the weight. Or we can also say that's the force we would have to use to lift it up, to oppose it. And this height is 1 meter. Oops, 1 meter. I'm not writing very well here. 1 meter. Oh, wait a minute. No, I'm off there. Sorry about that. I hope I didn't have too much of that off for you guys. Okay, so we got 1 meter off. And so if we want to lift that up, we can calculate it in 2 ways. And I'm going to show you they're the same thing. The potential energy is m times g times h. We already said that the weight, or excuse me, the mass of that brick is 2 kilograms. The g is 10 meters per second, approximated. And then the h is, let's see, we're lifting it 1 meter. So all of that is going to turn out to be 20, and it's a potential energy, so it's going to be 20 joules. Now there's another way to look at this. We can say that's the potential energy. Yes, indeed. It actually turns out it's the same as if I had done work. It's the same equation. There's my little exclamation mark there, right there. Okay, so we're going to say the work is equal to the force times the distance. Okay, what's the force? We're lifting this up with 20 newtons, right, which was this 2 kilograms times 10 meters per second, and then times 1 meter, and that turns out to be, well, Newton meters is actually the same as joules, so it's 20 joules. So, potential energy for me to lift that brick straight up 1 meter is 20 joules. And that actually, as it turns out, is the same as the force through the distance of lifting it straight up. Now, let's say that okay, so that's an important comment, or important concept. Now let's say that I had that same brick and I didn't want to. Can you see that if you have to push that brick straight up, you got to use a lot of force on it, right? I mean, that's 20 newtons. What if you could push it up, but you didn't have to put, like, I'm going to try and show you right here. If I took this brick and I lifted it straight up, I would have to put a lot of energy to lift it. But if I only, let's erase a little bit right here. Oh my, I just lost my ramp. Let's put it back. Okay. If I take this thing, can you see I'm pushing this way? And what that consists of is it's a part sideways motion, right? I'm pushing part way this way, and it's a part way upwards motion. That's what this tangential, this sort of up the ramp motion consists of, partly sideways, partly straight up. So what I'm doing when I push this box up the ramp, I am pushing it up, but only up a little bit at a time. Mostly I'm just pushing it sideways. So what that means is if the ramp is slick, I can push it up over a longer distance and I'll get it up to the same height. But at any given moment, I'm putting most of my force into it going sideways, right? Instead of lifting straight up. So I have to push it longer to get it all the way up, but I never have to push it as hard as if I had to just directly lift it straight up. So let's see how much force I actually have to put on it. Here we know we had to put 20 newtons on it. Well, if this ramp was 20 meters long, then I would only have to push on it with a force of 2 newtons in order for it to travel all the way up that ramp. So how much work would I be doing? Work is equal to force times distance. So the amount of work I'd have to do is 2 newtons times 10 meters. Oh, that's 20 newtons. That's the same as before when I lifted straight up. But hey, I only had to do 2 newtons of force, even though I had to lift it over, or I had to push it over a longer distance. So what your book is trying to say is that you can do, when you lift something directly, you have a big force through a little distance. When you push something up a ramp, you have a little force through a big distance, right? But however much energy it takes to get up there is the same, at least if the ramp is all slick, right? It's just that, you know, one is much easier for humans who don't like to use a lot of force. and that is to push things up a ramp. Now we're going to see a video of someone who has used exactly those kinds of ideas to unravel the mysteries of Stonehenge.
4,000 years ago, Stone Age Britons raised this mysterious monument, Stonehenge. Nobody knows how they did it, how they moved and stood these massive stones. It's a scientific mystery. This man swears he's cracked. He's building his own Stonehenge in his Flint, Michigan backyard to prove it. Wally Wallington's not a scientist, but he knows a thing or two about moving rocks.
That's a 300-pound block. This is a 1,600-pound block. Not too difficult.
He's a retired construction worker whose passion is moving heavy items. His feats always draw a crowd, mostly family.
I thought he was crazy. Who cares about moving blocks around? But then when you look at the magnitude of the weights that he's moving around, it is really impressive, and he's not using any equipment or anything.
In playing with blocks, Wally thinks he's discovered how Stonehenge was moved.
This is my first Stonehenge arch I permanently put in place. It's 3 blocks, they weigh over a ton each.
It's all based on a very simple technique.
I found a simple explanation for this, to move a block about the weight of a minivan, would be to place a stone underneath it. And once I balance on it, I can spin it. Of course, with that spin, you've seen I didn't go anywhere. But I got 2 handles on my lever, and I could place another stone on this side. Now, every time I spin a half rotation on each stone, I move the block horizontally, the distance between the stones. With my own output, I could move a 1-ton block 300 feet per hour.
Using this technique, he's moved everything from 1-ton blocks to buildings.
He moved up to a pole barn at one point, a 30 by 40 pole barn that he moved 300 feet for me, and it was more or less, you know, what else can we move? And he looked at me and says, hey, can we move your barn? And I said, sure, let's, you know. Next thing you know, it was 300 feet in the other direction onto another piece of property.
It can move barns, and Wally's betting it moves Stonehenge's 25-ton rocks. But raising these giants is a whole different puzzle.
This is 19,200 pounds. Yeah, it's 128 cubic feet of concrete.
Today, Wally hopes to solve it. He'll put one of his theories to the test and try to stand this 19,200-pound block by himself.
I've tried to do this without any mechanical machinery at all. I've used mostly sticks and stones for my equipment. No pulleys, no hoists, no metal levers. Just try to use gravity, too, I believe is my favorite tool. Whoop.
The first goal is getting this block 3 feet off the ground.
In order to move it up to this point, I just rock the block back and forth, adding weight to that end, and that opens a gap on this side, and just slide a board in. Then I add the weight to that end, there she goes, and slide a board in on this end.
This shoring box acts like a jack, slowly raising the block. It's 3 feet off the ground, but tomorrow is the big experiment, standing it up. The grandkids have taken the day off school, and the cameras are rolling.
Hey, you guys watch Papa. He's going to do something wild.
They're here to watch Granddad lift a block the weight of 2 bulldozers.
It's ready.
Yes, it is.
Here's how it's supposed to work.
The first thing I'm going to do here is release this temporary shoring I have set, and come over here, release some of my counterweights, and that's going to put the entire weight of the block on this rope. So then I'm going to release the rope, come back in, and the rope's going to be my brake. I'm going to guide it into the pit. The easiest way I can explain this is this is just a big teeter-totter, and I got the big kid on that end, and he's going to go down, this end's going up.
He believes in his technique, but he's had some setbacks in the past.
One day I got thrown over top of a block, and a couple times I had the blocks roll off the top and almost land on my feet. One time I knocked myself out cold on the concrete. And so it's been challenging. Okay. Are you ready? Yes. All right. Now just start spraying the sand. The sand will wash out and the block will start coming down.
Once the sand is washed from the pit, the block's own weight slowly stands it up.
Okay, finally, she's between the lines, guys. Looks good.
He did it.
Thank you, guys.
Raised a massive block using a technique so simple that Wally believes it must have been used to raise Stonehenge.
If they were to use this technique to raise the stones at Stonehenge, I believe they could have got it done with a lot smaller crew than anybody has imagined before.
It won't be long before this backyard is a little more crowded.
This is my first block in the circle. I plan to have 8 of them standing on end like that, all up 11 feet in height. The next one may be a little heavier. We're going to keep going a little further with it.
Until then, the only mystery that remains is this stone circle's name.
Wally's Wonder Circle.
How about the Wallington Circle?
What's that? Stonehenge Reloaded.
There you go.
Stonehenge Reloaded. There you go. That's not bad.
Okay, now we're going to go and experiment with a ramp. Okay, now on this ramp, what I've done is I've set this as, so you can have ice with no friction, or you can have wood, but we're going to choose ice so it's really slippery. Okay, now what I can do is well, first off, you'll notice this box. It has Fg, which is the force of gravity. That's its weight pulling it down. And clearly it's got see this Fn right there? I always hate it when professors say clearly because it's never that clear to me. But anyway, the N there stands for normal, which means essentially the straight back up force that's pushing on this box and keeping it from falling down. So gravity is the force that's pulling it down, and the normal force is the force being applied by the ice to push it back up. If we wanted to, I could show you the free body diagram, which is just an illustration of the forces altogether on the box. You see there's one force going down, gravity, one force going up, the normal force, and they balance one another, which is why it's just sitting there. Now, if we wanted this thing to move, you would expect to see some kind of force going sideways that would make it start to move. And as it turns out, we can make it do that. Look at that. See that little FA that's growing and it's starting to go up, and we've just pushed it against the wall. So that's where it bashed in there. Okay, so you have to kind of watch a little bit as I'm going to try and start applying a forward force. And oops, when I get it going too much, come here. Now you see that FW, that's the wall force. If I'm pushing too hard, the wall it'll push against the wall, and then the wall of course pushes back. Now I'm taking that wall force, so it's just going to 0. Now it's creeping back down. Now notice I'm trying hard to just hold it in place. It's really hard actually. That FA is the I dropped it is the applied force, and that is the force which I'm just barely pushing a little bit of applied force, and notice how it's a smaller force than that Fg. That has to do with, again, that idea that I'm just pushing a little bit vertically, and most of it is horizontal, and so it's a smaller force but through a larger distance. So you can go and play with this yourself. You can see that there's all sorts of things you can put. You can put a sleepy dog right there if you want to, and you can push your sleepy dog up there, or whatever you would like. So if you wanted to, you could put a frictional surface, and you can vary the friction. We're going to talk about this in the next chapter a little more, but if you have static friction, which you can increase, that's like little pieces of Velcro, just a sticky surface in some sense. And the only difference between static friction and kinetic friction is Static friction is what is happening when it's not moving, right? So, okay, I'm going to start pushing it. Look, I've got to push, hard, hard, hard. And then when it starts moving, the kinetic friction is actually lower. So once I get it going, then the kinetic friction makes it easier to push, and then, of course, I bash into the wall. You can have fun playing with this all by yourself. It's actually a great demonstration. Look at this one right here. I was messing around with it. I left it in the highly vertical position. If I make a low ramp, okay, I'm on ice again. And now notice my applied force right here. I've got my applied force. And as I'm pushing, the force gets, you can play with it and just watch how the applied force changes between when it's on the ramp and when it's not on the ramp. I do enjoy the Robot Moving Company, and if you would like to, you can play with the Robot Moving Company yourself. And it simply has to do with, okay, so let's go over here. I've just pressed the arrow keys, and I'm trying to nudge this dog into place. You can see all the forces. Oh, look at this sleepy dog, delivered successfully. And there's a daughter in the background. Okay, so that has been silenced. And now we have a refrigerator. We're going to push our refrigerator. Oh, we got to use the arrows. And okay, oh no! I've just gotten 0 points because I destroyed the refrigerator. Okay, so let's try the textbook now. I'm apparently not very good at video games. Here, okay, and so I'm pushing this. I think I'm pushing this down. And oh no! Stop. Okay, I just destroyed that. Okay, now I've got a mystery object. And notice, see the mass on it, and we know what kind of kinetic friction we've got, how much points I can have. We're going to push it a little bit. We're going to use the arrow keys. Okay, oh, okay. No, okay. Whew. Okay, at least it didn't go off the cliff. Okay, notice each time I'm applying a force, I'm doing work, and that work as I'm applying the force, this is all wasted work. If I did a hole in one, so it came right down and oh, there we go. Okay, so see the 600 points I would have gotten, and then it's there's the 103 extra, or actually 1034 extra joules. And so anyway, there's my total of 703 points. And if you would like, you can play this game yourself, and it's really fun.